Hello friends, throughout this course we have seen about equation of motion for longitudinal motion, equation of motions for lateral direction motions, various modes of longitudinal motions, that is phygoid and short period, your lateral direction modes, spiral, Dutch roll and roll. Then we saw about transfer functions and how the transfer function will respond to step input and impulse signal. We also saw stability augmentation system and how your required zeta and omega n will be changed using the stability augmentation system. Now, today we will be focusing on mode shapes, and what we will be learning what is the importance of mode shape and what information do we get from mode shapes. So, mode shapes we will be learning first longitudinal mode shapes, mode shapes and lateral directional mode shapes. So, let us first focus on longitudinal mode shapes. Longitudinal mode shape. Now, first question which comes into our mind is what is a mode shape? Now, mode shape is basically your relation between your longitudinal derivatives, that is the relation between your u, your alpha and theta. What will be the relationship or how they will affect each other in terms of magnitude and phase. What is the relation between these three variables in terms of magnitude and phase? So, the best way of deriving the relationship between these derivatives will be to use the longitudinal equation of motion, or you can say longitudinal equation of motion free from elevator, deflection and gust. As we have already seen while deriving transfer function and various modes of longitudinal motion, the derivatives or differential equation for longitudinal motion were u dot minus g theta into cos theta 1 plus x of u into u plus x tu into u plus x alpha into alpha plus x delta E into delta E w dot minus u1 q equals to minus g theta sin theta 1 plus zu into u plus z alpha into alpha plus z alpha dot into alpha dot plus zq into q plus z delta E into delta E. And third equation was q dot equals to mu into u plus mtu into u plus m alpha into alpha plus m alpha dot into alpha dot plus mq into q plus m delta E into delta E. This was already derived while we were deriving transfer function and phugoid and short period mode. Now, as we told, to derive the relationship between these longitudinal variables, you have to neglect the elevator inputs as well as any disturbance or gust. So, let us remove this or neglect this term due to delta E and making suitable substitution in this equation, as we know that alpha equals to W upon U. So, using this equation or using this formula, you can substitute the value of W in this equation and your equation will be in terms of alpha. So, making required substitution and neglecting delta E and taking Laplace transform of that, the equation will be of this sort. Xu into U of S minus x alpha into alpha of S plus G cos theta 1 into theta of S equals to 0 minus ZU U of S plus S into U1 minus Z alpha dot minus Z alpha into alpha of S plus bracket minus of ZQ plus U1 S plus G sin theta 1 into theta of S equals to 0 and minus mu U of S minus m alpha dot S plus m alpha into alpha of S plus S square minus mq S into theta S equals to 0. Any thrust derivatives which you encounter in this equation, either it is neglected or you can assume that it has already been incorporated in your derivatives here. Dividing this differential equation by theta s, we will get, because we want the relationship between these variables, we will get equation as S minus xu U of S by theta of S minus x of alpha alpha of S by theta of S equals to minus G cos theta 1 minus ZU U of S by theta of S plus S into U1 minus Z of alpha dot minus Z of alpha alpha of S upon theta of S equals to ZQ plus U1 S minus G sin theta 1, and your third equation will be minus mu U of S upon theta of S minus of m alpha dot S plus m alpha alpha of S by theta of S equals to minus S square plus mq S. You can write this differential equation in terms of matrix, and we have already seen while deriving transfer function, you can use that Cramer's rule to derive what will be the value of us upon theta of s, alpha s upon theta of s. As you can see, this has 3 equations and 2 variables. You can choose any of the 2 equations and solve for u of s upon theta of s, alpha s upon theta of s. So, representing it in a matrix form, we will get s minus xu minus mu using equation 1 and 3. This is equation 1, this is 2, this is 3. I am using equation 1 and 3, you can use any of the 2 equations. My matrix will be in the form minus x of alpha minus m alpha dot s plus m alpha into u of s upon theta of s, alpha of s divided by theta of s equals to minus g cos theta 1 and minus s square plus mq into s. Now, best way to derive the relationship between us and theta of s is using Cramer's rule. So, u of s upon theta of s will be determinant of replacing this first column by the value of this matrix, that is minus g cos theta 1 minus s square plus mqs minus x alpha minus of m alpha dot s plus mq divided by determinant of this matrix, my u x of alpha minus mu minus m alpha dot s plus m alpha. Now, the denominator in both the cases, that is u by s and theta by s and alpha by s upon theta by s will be same. So, determinant of this matrix will be, let us call it as D. D will be minus D will be minus m dot s square plus xu m alpha dot minus m alpha into s plus xu m alpha minus mu x alpha. Similarly, the numerator of this ratio will be, let me call this as n1. N1 will be x alpha x square plus m alpha dot g cos of theta 1 plus x alpha mq into s plus g cos theta 1 m of alpha. Similarly, you can derive numerator for alpha of s upon theta of s, which will be determinant of s minus xu minus mu, and replacing the second column by your matrix minus g cos theta 1 and minus s square plus mq s. Let me call this as n2, numerator 2. The value of n2 will be minus s cube plus mq plus xu into s square minus xu mqs minus mu g cos theta 1. Now I have got the relationship between u of s upon theta of s in terms of numerator and denominator, as well as alpha of s upon theta of s in terms of numerator and denominator. Now, the ratio of this will be in complex form. Since the value of s are complex, so you will be getting this ratio in terms of complex number. Let u of s upon theta of s be in some form of complex number, say numerator 1 plus j of omega n1 and d1 plus j of omega d1. So, the magnitude of this will be equals to root under n1 square plus omega n square divided by d1 square plus omega d1 square n1. Yes. And your phase will be tan inverse of omega n1 upon n1 minus phase tan inverse omega d1 upon d1. Now, using the values of longitudinal derivatives for a business jet airplane, I have already shared the derivatives on the forum. You can go and check the values of these derivatives. These derivatives were used for deriving the transfer function, as well as when we will be doing the numerical for this section, the same derivatives are used in both the section, transfer function as well as for mode shapes. You can go and check the forum. So, for the derivatives, longitudinal derivatives for a business jet aircraft, my values of this derivatives mq xu are my m alpha dot equals to 0.407, xu m alpha dot minus m alpha equals to 7.451, xu m alpha minus mu x of alpha equals to 0.0465. For u of s numerator n1, the coefficients which we calculated will be minus x of alpha equals to minus 8.46, m alpha dot g cos of theta 1 plus x of alpha mq equals to minus 20.985, g cos theta 1 m alpha equals to minus 238.336. These were for u of s. Alpha of s similarly, that is your numerator n2. The coefficients will be minus 1 mq plus x of u equals to minus 0.9485 minus XU MQ equals to minus 0.0070 minus MU G cos theta 1 equals to minus 0.0352. Using the derivatives, now we can calculate what will be the transfer function of longitudinal perturbed equation of motion, which we already derived while we were studying transfer function, which came in the form of AS4 plus BS cube plus CS square plus TS plus E. This was the characteristic equation of my longitudinal equation of motion. Now, substituting the derivatives, we have already shared on the forum. The value of A to E will be A equals to 675.9, B equals to 1371, C equals to 5459, D equals to 86.30 and E equals to 44.78. So, the roots of my characteristic equation will be lambda 1 and 2 equals to 1.008 plus minus 2.651 I, and lambda 3 4 equals to minus 0.0069 plus minus 0.0905 I. The ratio for u of s upon theta of s, substituting the value of derivatives, will get 8.46 s square minus 20.985 s minus 238.336 divided by 0.407 s square plus 7.451 s plus 0.0465. Now, substituting the value of s, that is roots of this characteristic equation. Now, as you know, this will be corresponding to your short period mode roots, and this will be corresponding to your fugoid mode. So, let us substitute the value of short period mode in my equation for deriving what will be the magnitude and phase of u of s upon theta of s. Substituting the value of short period mode roots, will get final value in terms of complex number will be minus 166.373 minus 10.42 I divided by minus 9.91 plus 17.5 I. This value at short period mode root. Now, magnitude of this complex number will be root under 166.373 square plus 10.42 square divided by 9.91 square plus 17.1 square, which will come about 8.28. Similarly, alpha of s upon theta of s was minus s cube minus 0.9485 s square minus 0.0070 s minus 0.0352 divided by, since the denominator was same, so this will be similar. 7.451 s plus 0.0465. The magnitude of alpha of s upon theta of s at your short period mode root will give me minus 14.55 plus 15.60 I divided by minus 9.91 plus 17.5 I. The magnitude of this will be equals to 1.0607, and phase of this will be phase of alpha of s upon theta of s equals to tan inverse 15.60 divided by minus 14.55 minus of tan inverse 17.5 divided by minus 9.91, which will be around 13.49 degrees. Now, as you can see, my initial velocity, which was 675 feet per second, this was my u1. U of s upon theta of s equals to magnitude of this is 8.28. When divided by your initial velocity u1, that is 675, you will get u of s upon u1 in terms of theta s 0.0122 theta, which is a very small quantity. So, now drawing the mode shape of this analysis for short period mode, this is a unit circle where of theta, as I saw during the analysis, your alpha upon theta, the magnitude was 1.067. So, the vector this of unit, this is a circle of unit radius. So, your magnitude of alpha will be 1.06 and at an angle of 13.49 degrees. So, at 13.49 degrees, your magnitude will be, this is 13.49 degrees, and your magnitude of this vector is 1.067. And u of s upon u1, u of s upon u1 in terms of theta is very small, 0.0122. So, we can neglect that part. Now, doing the same analysis for another root, that is phugoid mode root, which was phugoid mode root, which was minus 0.0069 plus minus 0.0905 I. Now substituting this value in your equation of us of s upon theta of s and alpha of s upon theta of s, magnitude of u of s upon theta of s while substituting the roots of phugoid mode, you will get minus 238.12 minus 1.88 I by minus 8.226 into 10 to the power of minus 3 plus 0.6738 I. The magnitude of this will be the magnitude of this complex number ratio, which will come about 353.37 u of s upon theta of s. Now dividing this by your initial velocity, that is u1, so u of s upon u1 in terms of theta will be 0.523 theta. Similarly, magnitude of alpha of s upon theta of s at phugoid mode root equals to 0.0401, and phase of u of s upon theta of s equals to tan inverse of minus 1.88 by minus of 238.12 minus tan inverse 0.673 by minus 8.226 into 10 to the power minus 3, which will come about 90 degrees. Now drawing the mode shape diagram for phugoid mode. This is a unity circle with theta as parameter. Your u upon u1 was 0.523 theta and angle of 90 degree, which will be represented by this vector. This is 0.523 theta and this was your 90 degree. And as you can see, the value of alpha in this case, alpha upon theta s in this case was very small. That is, alpha in terms of theta will be 0.0412 theta, which is very small, so you can neglect that. Now, as I was telling, the information which we get from mode shapes are, in case of phugoid mode, as you can see, since alpha is very small, so we can say that for phugoid mode approximation, alpha remains constant, whereas for short period mode, as you saw, u upon u1 was very small. So you can say while approximating short period mode, your velocity or speed remains constant. From the analysis, we can see that the short period mode takes place at constant speed, while phugoid mode takes place at constant angle of attack. Similar to analysis which we did for longitudinal equation of motion, we will be doing analysis for lateral direction equation of motion. So, we will be seeing the lateral direction mode shapes. Lateral, this is our directional mode shapes. we will be finding a relationship between your beta, psi, phi and psi in terms of magnitude and phase. So, the best way of deriving that will be writing your lateral direction differential equation and taking Laplace transform of that, provided that you have neglected aileron deflection, rudder deflection and any gust. Your differential equation in Laplace transform will be Su minus y of beta into beta of s minus s yp plus g cos theta 1 into phi of s plus s u1 minus yr into psi of s equals to 0 minus L beta into beta of s plus s square minus LP s into phi of s minus s square A1 plus SLR into psi of s equals to 0 minus n beta into beta of s minus s square B1 plus NPS into phi of s plus s square minus s and r into psi of s equals to 0. Now, you can rearrange this equation by dividing the whole differential, 3 differential equation by beta of s. You will get SYP minus of SYP plus g cos theta 1 into phi of s upon beta of s plus s u1 minus y of r into psi of s upon beta of s equals to minus s u1 minus s u1 minus y of beta. S square minus LPS into phi of s upon beta of s minus s square A1 plus SLR into psi of s upon beta of s equals to L beta. And third, minus s square beta 1 plus NP NPS phi of s upon beta of s plus s square minus s and r into psi of s upon beta of s equals to n beta. You can use any 2 equations, since it is a 2 variable equation and you have 3 equations. So, you can take any 2 of these and you can write that in matrix form. And we have already seen for longitudinal case as well, while we are doing transfer functions, you can derive first variable by using Cramer's rule. So, I am directly writing your transfer function, which will be phi of s upon beta of s, taking equation 2 and 3. it will be determinant of L beta n beta minus S square A1 plus SLR S square minus SNR divided by determinant S square LPS minus S square B1 plus NPS minus S square A1 plus SLR and S square minus S and R, which will give S to the power of 4 1 minus A1 B1 minus S cube NR plus LP plus LR B1 plus NP A1 plus NR LP S square minus NR NP S square. This is your denominator, the determinant of denominator. The numerator will be N1 S square L beta minus S NR L beta plus N beta A1 S square plus N beta LR S. So, phi of S upon beta of S will be S into L beta plus N beta A1 plus N beta LR minus NR L beta divided by S square 1 minus A1 B1 S into minus S NR plus LP plus LR B1 plus NP A1 plus NR LP minus LR NP. Similarly, psi of S upon beta of S will be S into N beta plus B1 L beta plus L beta NP minus LP N beta divided by S into S square 1 minus A1 B1 minus S NR plus LP plus LR B1 plus NP A1 plus NR LP minus LR NP. Using the value of lateral direction derivatives, you will get the transfer function or the ratio between psi of S upon beta of S and phi of S and beta of S and psi of S and beta of S as phi of S upon beta of S equals to minus 4.146 S minus 0.0273 by S into S square plus 0.541 S plus 0.04 0.52, and psi of s upon beta of s will be 2.59 s plus 1.130 divided by s into s square plus 0.541 s plus 0.0452. Now, using this lateral direction derivatives, you will get the characteristic roots of lateral directional equation of motion, which will be fourth order equation. So, it will be having 4 roots. So, the roots of that characteristic equations are, the values are already given in the sheet which I have shared on the forum. You can go and check the values. Lambda 1 will be minus 0.00101, lambda 2 equals to minus 0.507, and lambda 3 comma 4, that will be a complex conjugate, it is minus 0.0580 plus minus 1.617 I. Now, we have got the ratios between psi of s and beta of s, and phi of s and beta of s, and psi of s and beta of s, and evaluating each values at different roots. This will be corresponding to your spiral mode, this will be corresponding to your roll mode, and this will be corresponding to your Dutch roll. So, evaluating these ratios at each of these roots, you will get mode shape for different modes corresponding to spiral, corresponding to roll, and corresponding to Dutch roll. Let us first see the mode shape regarding to spiral mode. Mode shape for spiral. The root, spiral root was minus 0.00101. Substituting this value in your ratio of phi s upon beta s and psi s upon beta of s will give phi of s upon beta of s at lambda equals to minus 0.00101. Magnitude of this will be minus 0.0231 divided by minus 0.0000451, which will be 513.33, and phase of this will be 0 degree, means both phi and beta are in phase. Similarly, psi of s upon beta of s at lambda, magnitude of this at lambda equals to minus 0.00101 will give me 1.127 divided by minus 0.000451, which is equal to 24,988.9. But the phase here are apart by 180 degree, or they are out of phase by 180 degree. Phase of psi of s upon beta of s equals to 180 degree. So, while drawing the mode shape for spiral mode, this will be unit circle with psi s parameter. From this ratio, your beta of s, beta will be 1 by 24,988.9, which will be into psi, which will be somewhere around 0.0004 psi, and your phi of phi will be 513.33 into beta, and since beta is 0.0004 psi, so phi and psi relationship between them will be phi will be 0.0205 psi. Now we saw that the phase difference between beta and psi was 180 degree, whereas the phase for psi and beta was 0. So when plotting this magnitude and phase in my mode shape, we will be getting magnitude of phi with respect to psi as 0.025, but phase will be 180 degree. Say somewhere here, this is 0.05 psi. Phi will be equal and phase will be 180 degree, and this is very small. You can neglect it, it will be very close to origins, you can neglect this. Now from this analysis, what we came to know that in case of spiral mode, your beta is very small, since the ratios are very large. So beta or side slip angle plays a very insignificant role in spiral mode, and as you can see, the relation between phi and psi is 0.025 with phase difference of 180 degree. So it can be plotted with as seen in spiral mode. So from this analysis, we can infer that your beta is very small, since the ratios are very large, so you can neglect that, and spiral mode is majorly concerned with your slight slip angle, since the ratio of psi s upon beta of s is very large. Now second analysis will be for roll mode. So mode shape for roll. The roots was given by minus 0.507. Now when substituting this value in the ratios of phi upon beta s and psi upon beta s, you will get phi s upon beta s as 147.16 with phase difference 0, and psi of s upon beta of s, magnitude of this will be 12.98 with phase difference of 180 degree. Similarly, we can write that beta in terms of phi will be 0.00685 and your psi will be 0.0885. When plotting this in mode shape for roll mode, a unit circle in terms of phi, the magnitude will be a small value for beta and phi relation. This will be 0.00685, and your psi and beta relation, psi and phi relation by 0.0885. Now from this analysis, you can see for rolling mode, phi is a dominant, the bank angle is a dominant for roll mode, and the last analysis will be for your Dutch roll. Substituting the value of Dutch roll in these ratios, you will be getting magnitude of phi s upon beta s as 1.54 with angle phi of beta s as minus 165.4 degree. So there will be two magnitude and a phase angle because these are complex roots. Similarly, psi of s upon beta of s magnitude will be 0.0885. 0.99 and angle of psi of s upon beta of s equals to minus 154.07. When drawing the mode shape of this Dutch roll, a unit circle in terms of phi, you will get beta equals to 0.65 phi and psi equals to 0.64 phi. Since this is a direct relation, so this will be at an angle of minus 165 degree. This is minus 165 degree and magnitude will be 0.65 phi. And this will be, since psi is obtained by 0.99 into beta and beta is already 0.65 into phi, so the angle which you will be getting is 360 minus of this angle 165.4 minus 154.07, which will be around 40.50 degree. So your magnitude will be, this will be 40.50 degree and your magnitude will be 0.645. So this was all regarding to mode shape, and I hope you enjoyed this lecture. Thank you.